हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज हम करने वाले हैं क्लास 11th यूनिट 12 सम बेसिक प्रिंसिपल एंड टेक्निक्स। और आपको पता है आज ये क्लास 11th का लास्ट चैप्टर है ऑडियो बुक का, जो बाकी रह गया था। इसको कंप्लीट कर दूंगी एंड देन आफ्टर आपकी पार्ट 2 भी पूरी एक वीडियो सारे चैप्टर्स का बना करके मैं जल्दी से अपलोड कर दूंगी। सो चलिए, टाइम वेस्ट नहीं करना है बच्चों। अगर आपको लगता है कि ऑडियो बुक्स आपकी हेल्प कर रही हैं तो प्लीज इसको लाइक कीजिएगा, और अगर आप मेरे चैनल पे नए हैं तो इसको सब्सक्राइब कीजिएगा। और एक काम और करना है, आपको अपने दोस्तों के साथ में ज्यादा से ज्यादा शेयर करना है ताकि मुझे भी मोटिवेशन मिले एंड साथ ही साथ आपके दोस्तों की भी हेल्प हो। जब आप लोगों के अच्छे अच्छे कमेंट्स आते हैं ना, तो मुझे पढ़ करके बहुत अच्छा लगता है कि ये ऑडियो बुक्स आपकी इतनी हेल्प कर रही हैं रिवीजन में। सो बच्चों, प्लीज इसको अपने दोस्तों के साथ भी शेयर करिएगा एंड खुद भी अपने रिवीजन में ज्यादा से ज्यादा यूज कीजिएगा। चलिए स्टार्ट करते हैं सम बेसिक प्रिंसिपल एंड टेक्निक्स। In the previous unit, you have learned that the element carbon has a unique property called catenation, due to which it forms covalent bonds with other carbon atoms. It also forms covalent bonds with atoms of other elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus, and halogens. The resulting compounds are studied under a separate branch of chemistry called organic chemistry. This unit incorporates some basic principles and techniques of analysis required for understanding the formation and properties of organic compounds. 12.1 General Introduction. Organic compounds are vital for sustaining life on Earth and include complex molecules like genetic information bearing deoxyribonucleic acid and proteins that constitute essential compounds of our blood, muscles, and skin. Organic compounds appear in materials like clothing, fuels, polymers, dyes, and medicines. These are some of the important areas of application of these compounds. Science of organic chemistry is about 200 years old. Around the year 1780, chemists began to distinguish between organic compounds obtained from plants and animals and inorganic compounds prepared from mineral sources. Berzelius, a Swedish chemist, proposed that a vital force was responsible for the formation of organic compounds. However, this notion was rejected in 1828 when F. Wohler synthesized an organic compound urea from an inorganic compound, ammonium cyanate, NH4CNO, that is ammonium cyanate. On heating, it is forming NH2CONH2, that is urea. The pioneering synthesis of acetic acid by Kolbe in 1845 and that of methane by Berthelot in 1856 showed conclusively that organic compounds could be synthesized from inorganic sources in a laboratory. The development of electronic theory of covalent bonding ushered organic chemistry into its modern shape. 12.2 Tetravalence of carbon shapes of organic compounds. 12.2.1 The shapes of carbon compounds. The knowledge of fundamental concepts of molecular structures helps in understanding and predicting the properties of organic compounds. You have already learned theories of valency and molecular structure in Unit 4. Also, you already know that tetravalence of carbon and the formation of covalent bonds by it are explained in terms of its electronic configuration and the hybridization of s and p orbital. It may be recalled that formation and the shapes of molecules like methane, ethene, ethine are explained in terms of the use of sp3, sp2 and sp hybrid orbitals by carbon atoms in the respective molecules. Hybridization influences the bond length and bond enthalpy in compounds. The sp hybrid orbitals contain more s characters and hence it is closer to its nucleus and forms shorter and stronger bonds than sp3 hybrid orbital. The sp2 hybrid orbital is intermediate in s character between sp and sp3 and hence the length and enthalpy of the bond it forms are also intermediate between them. The change in hybridization affects the electronegativity of carbon. The greater the s character of the hybrid orbitals, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50% s character is more electronegative than that of sp2 or sp3 hybridized orbital. This relative electronegativity is reflected in several physical and chemical properties of the molecules concerned, about which you will learn in later units. 12.2.2 Some characteristics features of pi bonds. In a pi bond formation, parallel orientation of the two p orbitals on adjacent atoms is necessary for a proper sideways overlap. Thus, in H2C double bond CH2 molecule oil, the atoms must be in the same plane. The p orbitals are mutually parallel and the p orbitals are perpendicular to the plane of the molecule. Rotation of one CS2 fragment with respect to other interferes with maximum overlap of p orbitals, and therefore such rotation about carbon-carbon double bond is restricted. The electron charge cloud of the pi bond is located above and below the plane of bonding atoms. This results in the electrons being easily available to the attacking reagents. In general, pi bond provides the most reactive centers in the molecules containing multiple bonds. 12.3 Structural representations of organic compounds. 12.3.1 Complete condensed and bond line structural formulas. The structures of organic compounds are represented in several ways. The Lewis structure or dot structure, dash structure, condensed structure, and bond line structural formulas are some of the specific types. The Lewis structures, however, can be simplified by representing the two electron covalent bond by a dash. Such a structural formula focuses on electrons involved in bond formation. A single dash represents a single bond. Double dash is used for double bond, and a triple dash represents triple bond. Lone pairs of electrons on heteroatoms, example oxygen, nitrogen, sulfur, halogen, etc., may or may not be shown. Thus, ethane, ethene, ethyne, and methanol can be represented by the following structural formulas. Such structural representations are called complete structural formulas. You can see here the structures. These structural formulas can be further abbreviated by omitting some or all of the dashes representing covalent bonds and by the indicating the number of identical groups attached to an atom by a subscript. The resulting expression of the compound is called a condensed structural formula. Thus, ethane, ethene, ethyne, and methanol can be written as, here you can see. Similarly, CS3, CS2, 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 CS3 can be further condensed to CS3, CS2 whole 6 CS3. For further simplification, organic chemists use another way of representing the structures in which only lines are used. In this bond line structural representation of organic compounds, carbon and hydrogen atoms are not shown, and the lines representing carbon-carbon bonds are drawn in a zigzag fashion. The only atoms specifically written are oxygen, chlorine, nitrogen, etc. The terminals denote methyl groups unless indicated otherwise by a functional group, while the line junctions denote carbon atoms bonded to appropriate number of hydrogen required to satisfy the valency of the carbon atoms. Some of the examples are represented as follows. Number 1, 3-methyl-octane can be represented in various forms. Here you can see A form, B form, and second, various ways of representing 2-bromobutane here, A, B, and C. In cyclic compounds, the bond line formulas may be given as follows. You can see cyclopropane, cyclopentane, cyclohexane. 12.3.2 Three-dimensional representation of organic molecules. The 3D structure of organic molecules can be represented on paper by using certain conventions. For example, by using solid and dashed wedge formula, the 3D image of molecule form a two-dimensional picture can be perceived. In this formulas, the solid wedge is used to indicate a bond projecting out of the plane of a paper towards the observer. The dashed wedge is used to depict the bond projecting out of the plane of the paper and away from the observer. Wedges are shown in such a way that the broad end of the wedge is towards the observer. The bonds lying in plane of the paper are depicted by using a normal line. 3D representation of methane molecule on paper has been shown in figure 12.1. Here you can see. Molecular models. Molecular models are physical devices that are used for a better visualization and perception of three-dimensional shapes of organic molecules. These are made of wood, plastic, or metal and are commercially available. Commonly, three types of molecular models are used. Number 1, framework model. Number 2, ball and stick model. And number 3, space filling model. In the framework model, only the bonds connecting the atoms of molecules and not the atoms themselves are shown. This model emphasizes the pattern of bonds of a molecule while ignoring the size of atoms. In the ball and stick model, both the atoms and the bonds are shown. Balls represent atoms and the sticks denotes a bond. Compounds containing C double bond C can best be represented by using springs in place of sticks. These models are referred to as a ball and spring model. The space filling model emphasizes the relative size of each atom based on its van der Waals radius. Bonds are not shown in this model. It conveys the volume occupied by each atom in the molecule. In addition to these models, computer graphics can also be used for molecular modeling. See this framework model, ball and stick model, and space filling model. 12.4 Classification of organic compounds. The existing large number of organic compounds and their ever increasing number has made it necessary to classify them on the basis of their structures. Organic compounds are broadly classified as follows. Organic compounds, two parts, is cyclic or open chain compounds, and second is cyclic or closed chain ring compounds. Now it is having the two parts, alicyclic compounds and aromatic compounds. Now alicyclic compounds have the two parts, homocyclic or carbocyclic, and heterocyclic compound and non-aromatic. And the aromatic compounds has the three parts, benzenoid compounds, non-benzenoids, and heterocyclic aromatic compounds. Number 1, acyclic or open chain compounds. These compounds are also called as aliphatic compounds and consist of straight or branch chain compounds. For example, isobutane, acetaldehyde, acetic acid. See the structures. Number 2, cyclic or closed chain or ring compounds. A. Alicyclic compounds. Alicyclic or aliphatic cyclic compounds contain carbon atoms joined in the form of a ring. Sometimes atoms other than carbon are also present in the ring. Heterocyclic. Tetrahydrofuran given below is an example of this type of compound. See all these compounds. These exhibit some of the properties similar to those of aliphatic compounds. B. Aromatic compounds. Aromatic compounds are special types of compounds. You will learn about these compounds in detail in Unit 13. These includes benzene and other related ring compounds, benzenoid. Like alicyclic compounds, aromatic compounds may also have heteroatom in the ring. Such compounds are called heterocyclic aromatic compounds. Some of the examples of various types of aromatic compounds are benzenoid aromatic compounds, benzene, aniline, ethylene, and non-benzenoid compound. It has tropone. Heterocyclic aromatic compounds, it has furan, thiophene, and pyridine. Organic compounds can also be classified on the basis of functional groups into families or homologous series. 12.4.1 Functional group. The functional group is an atom or a group of atoms joined to the carbon chain which is responsible for the characteristic chemical properties of the organic compounds. The example are hydroxyl group, aldehyde group, and carboxylic acid group. 12.4.2 Homologous series. A group or a series of organic compounds each containing a characteristic functional group forms a homologous series, and the members of the series are called homologues. The members of homolog series can be represented by general formula, molecular formula, and the successive members differ from each other in molecular formula by a CH2 unit. There are a number of homologous series of organic compounds. Some of these are alkanes, alkenes, alkynes, haloalkanes, alkenols, alkenols, alkenones, alkanoic acid, amines, etc. It is also possible that a compound contains two or more identical or different functional groups. This gives rise to polyfunctional compounds. 12.5 Nomenclature of organic compounds. Organic chemistry deals with millions of compounds in order to identify them. A systematic method of naming has been developed and is known as the IUPAC, that is International Union of Pure and Applied Chemistry System of Nomenclature. In this systematic nomenclature, the names are correlated with the structure such that the reader or listener can deduce the structure from the name. Before the IUPAC system of nomenclature, however, organic compounds were assigned named based on their origin or certain properties. For instance, citric acid is named so because it is found in citrus food, and the acid found in red ant is named as formic acid since the Latin word for ant is formica. These names are traditional and are considered as trivial or common names. Some common names are followed even today. For example, Buckminster fullerene is a common name given to the newly discovered C60 cluster, a form of carbon, noting its structural similarity to geodesic domes popularized by the famous architect R. Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematics names are lengthy and complicated. Common names of some organic compounds are given in table 12.1. See this table. I am reading the common name. You can see the structure here. Methane, N-butane, isobutane, neopentane, N-propyl alcohol, formaldehyde, acetone, chloroform, acetic acid, benzene, and anisole, aniline, and acetophenone, and ethyl methyl ether. 12.5.1 The IUPAC system of nomenclature. A systematic name of an organic compound is generally derived by identifying the parent hydrocarbon and the functional group attached to it. See the example given below. This is the functional group, this is the branch, this is the functional group, and this is the parent chain. By further using prefixes and suffixes, the parent name can be modified to obtain the actual name. Compounds containing carbon and hydrogen only are called hydrocarbons. A hydrocarbon is termed saturated if it contains only carbon-carbon single bonds. The IUPAC name for a homologous series of such compounds is alkane. Paraffin was the earlier name given to these compounds. Unsaturated hydrocarbons are those which contain at least one carbon-carbon double or triple bond. 12.5.2 IUPAC nomenclature of alkanes. First is straight chain hydrocarbons. The names of such compounds are based on their chain structure and end with suffix "ane" and carry a prefix indicating the number of carbon atoms present in the chain, except from CH4 to C4H10, where the prefixes are derived from trivial names. The IUPAC names of some straight chain saturated hydrocarbons are given in table 12.2. The alkanes in table 12.2 differ from each other by merely the number of CH2 groups in the chain. They are homologous of alkane series. See this: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, icosane, and triocontane. C30H62 it is. Branch chain hydrocarbons. In a branch chain compound, small chains of carbon atoms are attached at one or more carbon atoms of the parent chain. The small carbon chains are called alkyl groups. For example, you can see here A and B. In order to name such compounds, the names of alkyl groups are prefixed to the name of parent alkane. An alkyl group is derived from a saturated hydrocarbon by removing a hydrogen atom from carbon. Thus, CH4 becomes CH3 and is called methyl group. An alkyl group is named by substituting "-ile" for "-ane" in the corresponding alkane. Some alkyl groups are listed in table: methane, methyl, ethane, ethyl, propane, propyl, butane, butyl, decane, decyl. Abbreviations are used for some alkyl groups. For example, methyl is abbreviated as Me, ethyl is Et, propyl is PR, and butyl is Bu. The alkyl groups can be branched also. Thus, propyl and butyl groups can have branched structure as shown below. See this structure. So many structures are there. Common branched groups have specific trivial names. For example, the propyl groups can either be N-propyl group or isopropyl group. The branched butyl groups are called secondary butyl, isobutyl, and tertiary butyl group. We also encounter the structural unit CH2C, CH3 whole thrice, which is called neopentyl group. Nomenclature of branch chain alkanes. We encounter a number of branch chain alkanes. The rules for naming them are given below. Number 1. First of all, the longest carbon chain in the molecule is identified. In the example given below, the longest chain has 9 carbons and it is considered as the parent or root chain. Selection of parent chain as shown in second is not correct because it has only 8 carbons. See this and this. So this one is correct. 2. The carbon atoms of the parent chain are numbered to identify the parent alkane and to locate the positions of the carbon atoms at which branching takes place due to the substitution of alkyl group in place of hydrogen atoms. The numbering is done in such a way that the branched carbon atoms get the lowest possible numbers. Thus, the numbering in the above example should be from left to right, branching at carbon atoms 2 and 6, and not from right to left, giving numbers 4 and 8 to the carbon atoms at which branches are attached. See this. Third, the names of alkyl groups attached as a branch are then prefixed to the name of the parent alkane and positions of substituent is indicated by the appropriate numbers. If different alkyl groups are present, they are listed in alphabetical orders. Thus, name for the compound shown above is 6-ethyl 2-methyl nonane. Note, the numbers are separated from the groups by hyphens and there is no break between methyl or nonane. Fourth, if 2 or more identical substituent groups are present, then the numbers are separated by commas. The names of identical substituents are not repeated. Instead, prefixes such as di, tri, tetra, penta, hexa, etc. are used. While writing the name of the substituents in alphabetical order, these prefixes, however, are not considered. Thus, the following compounds are named as 2,4 dimethylpentane, 2,2,4 trimethylpentane, 3-ethyl 4,4 dimethylheptane. Fifth, if the two substituents are found in equivalent position, the lower number is given to the one coming first in the alphabetical listing. Thus, the following compound is 3-ethyl 6-methyl octane and not 6-ethyl methyl octane. See this. 6. The branched alkyl groups can be named by following the above mentioned procedures. However, the carbon atom of the branch that attaches to the root alkane is numbered 1 as exemplified below. The name of such branched chain alkyl group is placed in parentheses while naming the compound. While writing the trivial names of substituents in alphabetical order, the prefixes iso and neo are considered to be the part of the fundamental name of alkyl group. The prefixes secondary and tertiary are not considered to be the part of the fundamental name. The use of iso and related common prefixes for naming alkyl groups is also allowed by the IUPAC nomenclature as long as these are not further substituted. In multi-substituted compounds, the following rules may also be remembered. If there happens to be two chains of equal size, then that chain is to be selected which contains more number of side chains. After selections of the chain, numbering is to be done from the end closer to the substituent. See these structures. Cyclic compounds. A saturated monocyclic compound is named by prefixing cyclo to the corresponding straight chain alkane. If side chains are present, then the rules given above are applied. Name of some cyclic compounds are given below. See these: cyclopentane, 1,methyl 3-propyl cyclohexane, and 3-ethyl 1,1 dimethyl cyclohexane. 12.5.3 Nomenclature of organic compounds having functional groups. A functional group, as defined earlier, is an atom or a group of atoms bonded together in a unique manner, which is usually the site of chemical reactivity in an organic molecule. Compounds having the same functional group undergo similar reactions. For example, CH3OH, CH3CH2OH, and CH3 whole twice CHOH, all having OH functional group, liberate hydrogen on reaction with sodium metal. The presence of functional groups enables systemization of organic compounds into different classes. Examples of some functional groups with their prefixes and suffixes along with some examples of organic compounds possessing these are given in table 12.4. First of all, the functional group present in the molecule is identified, which determines the choice of appropriate suffix. The longest chain of carbon atoms containing the functional group is numbered in such a way that the functional group is attached at the carbon atom possessing lowest possible number in the chain. By using the suffix as given in table 12.4, the name of the compound is arrived at. In the case of polyfunctional compounds, one of the functional group is chosen as the principal functional group and the compound is then named on that basis. The remaining functional groups, which are subordinate functional groups, are named as substituents using the appropriate prefixes. The choice of principal functional group is made on the basis of order of preference. The order of decreasing priority for some functional group is COOH, SO3H, COR, COCl, CONH2, CN, HCO, CO, OH, NH2, C double bond C, C triple bond C. The R-C6H5 halogens, NO2, alkoxy, etc. are always prefixes, some prefix substituents. Thus, a compound containing both an alcohol and keto group is named as hydroxyalkanone, since the keto group is preferred to the hydroxyl group. For example, HOCH2CH2 whole thrice CH2COCH3 will be named as 7-hydroxyheptane 2-one and not as 2-oxoheptane 7-ol. Similarly, BrCH2CH2 is named as 3-bromoprop 1-ene, not 1-bromoprop 2-ene. If more than one functional group of the same type are present, their number is indicated by adding di, tri, etc. before the class suffix. In such cases, the full name of the parent alkane is written before the class suffix. For example, CH2OH is named as ethane 1,2 diol. However, the ending Ne of the parent alkane is dropped in the case of compounds having more than one double bond or triple bond. For example, buta 1,3 diene. See the structure. See this table 12.4, some functional groups and classes of organic compounds. Classes of compounds, functional group, structure, IUPAC group prefix, IUPAC group suffix, and examples. (12.5.4) Nomenclature of substituted benzene compounds. For IUPAC nomenclature of substituted benzene compounds, the substituent is placed as prefix to the word benzene as shown in the following examples. However, common names written in bracket below of many substituted benzene compounds are also universally used. methylbenzene, toluene, methoxybenzene, anisole, aminobenzene, aniline, nitrobenzene, and bromobenzene. If benzene ring is desubstituted, the position of substituent is defined by numbering the carbon atoms of the ring such that the substituents are located at the lowest numbers possible. For example, the compound B named as 1,3 dibromobenzene and not as 1,5 dibromobenzene. In this trivial system of nomenclature, the terms ortho, meta, and para are used as prefixes to indicate the relative positions 1, 2, 1, 3, and 1, 4 respectively. Thus, 1, 3 dibromobenzene B is named as meta dibromobenzene. Meta is abbreviated as M, and the other isomers of dibromobenzene 1, 2A and 1, 4C are named as ortho or just O and para or just P, dibromobenzene respectively. For tri or higher substituted benzene derivatives, these prefixes cannot be used and the compounds are named by identifying the substituent positions on the ring by following the lowest locant rule. In some cases, common name of benzene derivatives is taken as the base compound. Substituent of the base compound is assigned number 1 and then the direction of numbering is chosen such that the next substituent gets the lowest number. The substituents appear in the name in alphabetical order. Some examples are given below. 1-chloro, 2,4 dinitrobenzene, 2-chloro, 1-methyl, 4-nitrobenzene, 2-chloro, 4-methyl anisole, 4-ethyl, 2-methyl aniline, 3,4 dimethyl phenol. When a benzene ring is attached to an alkane with a functional group, it is considered as substituent instead of a parent. The name for benzene as substituent is phenyl, C6H5, also abbreviated as PH. 12.6 Isomerism. The phenomena of existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism. Such compounds are called as isomers. The following flowchart shows different types of isomerism. 12.6.1 Structural isomerism. Compounds having the same molecular formula but different structures, manners in which atoms are linked are classified as structural isomers. Some typical examples of different types of structural isomerisms are given below. Number 1, chain isomerism. When two or more compounds have similar molecular formula but different carbon skeletons, these are referred to as chain isomers and the phenomena is termed as chain isomerism. For example, C5H12 represents 3 compounds: pentane, isopentane, neopentane. Number 2, position isomerism. When two or more compounds differ in the position of substituent atom or functional group on the carbon skeleton, they are called position isomers, and this phenomena is termed as position isomerism. For example, the molecular formula C3H8O represents 2 alcohol, propane 1-ol, propane 2-ol. Third, functional group isomerism. Two or more compounds having the same molecular formula but different functional groups are called functional isomers, and this phenomena is termed as functional group isomerism. For example, the molecular formula C3H6O represents an aldehyde and a ketone. Isomerism 2 types: structural and stereoisomerism. Structural isomerism 4 main types: chain isomerism, position isomerism, functional group isomerism, and metamerism. And stereoisomerism is having the 2 types: geometrical and optical isomerism. Fourth is metamerism. It arises due to different alkyl chains on either side of functional group in the molecule. For example, C4H10O represents methoxypropane and ethoxyethane. 12.6.2 Stereoisomerism. The compounds that have the same constitution and sequence of covalent bonds but differ in relative positions of their atoms or groups in space are called stereoisomers. This special type of isomerism is called as stereoisomerism and can be classified as geometrical and optical isomerism. 12.7 Fundamental concepts in organic reaction mechanism. In an organic reaction, the organic molecule, also referred as substrate, reacts with an appropriate attacking reagent and leads to formation of one or more intermediates and finally products. The general reaction is depicted as below: organic molecule, attacking reagent, forming the intermediate, and then after the products. Intermediate can form the byproducts also. Substrate is that reactant which supplies carbon to the new bond and the other reactant is called reagent. If both the reactants supply carbon to the new bond, then choice is arbitrary, and in that case the molecule on which attention is focused is called substrate. In such a reaction, a covalent bond between two carbon atoms are carbon and some other atom is broken and a new bond is formed. A sequential account for each step describing details of electron movement. Energetics during bond cleavage and bond formation and the rates of transformation of reactants into products, kinetics is referred to as reaction mechanism. The knowledge of reaction mechanism helps in understanding the reactivity of organic compounds and in planning a strategy for their synthesis. In the following sections, we shall learn some of the principles that explains how these reactions takes place. 12.7.1 Fission of covalent bond. A covalent bond can get cleaved either by heterolytic cleavage or by homolytic cleavage. In heterolytic cleavage, the bond breaks in such a fashion that the shared pair of electron remains with one of the fragments. After heterolysis, one atom has a sextet electronic structure and a positive charge, and the other a valence octet with at least one lone pair and a negative charge. Thus, heterolytic cleavage of bromomethane will give CH3 positive and Br negative as shown below. A species is having a carbon atom possessing sextet of electrons and a positive charge is called a carbocation, earlier called carbonium ion. The CH3 positive ion is known as methyl cation or methyl carbonium ion. Carbocations are classified as primary, secondary or tertiary depending on whether 1, 2 or 3 carbons are directly attached to the positively charged carbon. Some other examples of carbocations are CH3 CH2 positive with ethine cation are primary carbocation, CH3 whole twice CH positive isopropyl cation, a secondary carbocation, and a CH3 whole thrice C positive, that is tertiary butyl cation or tertiary carbocation. Carbocations are highly unstable and reactive species. Alkyl groups directly attached to the positively charged carbon stabilize the carbocations due to inductive and hyperconjugation effects, which you will be studying in the sections 12.7.5 and 12.7.9. The observed order of carbocation stability is CH3 positive is less than, CH3 CH2 positive is less than, CH3 whole twice CH positive is less than, CH3 whole thrice C positive. These carbocations have trigonal planar shape with positively charged carbon being sp2 hybridized. Thus, the shape of CH3 positive may be considered as being derived from the overlap of 3 equivalent carbon hybridized orbitals with one s orbital of each of 3 hydrogen atoms. Each bond may be represented as C sigma bond. The remaining carbon orbital is perpendicular to the molecular plane and contains no electrons. The heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. For example, when group Z attached to the carbon leaves without electron pair, the methyl anion is formed. Such a carbon species carrying a negative charge on carbon atom is called carbanion. Carbon in carbanion is generally sp3 hybridized and its structure is distorted tetrahedron as shown in figure 12.3. See this 12.3 figure. Carbanions are also unstable and reactive species. The organic reactions which proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reactions. In homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atoms. Thus, in homolytic cleavage, the movement of a single electron takes place instead of an electron pair. The single electron movement is shown by half-headed, that is fishhook curved arrow. Such cleaved results in the formation of neutral species atom or group which contains an unpaired electron. These species are called free radicals. Like carbocations and carbanions, free radicals are also very reactive. A homolytic cleavage can be shown as alkyl radicals are classified as primary, secondary or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. Organic reactions which proceed by homolytic fission are called free radical or homopolar or non-polar reactions. 12.7.2 Substrate and reagent. Ions are generally not formed in the reactions of organic compounds. Molecules as such participate in the reaction. It is convenient to name one reagent as substrate and other as reagent. In general, a molecule whose carbon is involved in new bond formation is called substrate and the other one is called reagent. When carbon-carbon bond is formed, the choice of naming the reactant as substrate and reagent is arbitrary and depends on molecule under observation. Number 1, you can see this reaction. Number 2, you can see this reaction. Nucleophiles and electrophiles. Reagents attack the reactive site of the substrate. The reactive site may be electron deficient portion of the molecule. Example, an atom with incomplete electron shell or the positive end of the dipole in the molecule. If the attacking species is electron rich, it attacks these sides. If attacking species is electron deficient, the reactive site for it is that part of the substrate molecule which can supply electrons. Example, pi electrons in a double bond. A reagent that brings an electron pair to the reactive site is called nucleophile, that is nucleus seeking, and the reaction is then called nucleophilic. A reagent that takes away an electron pair from reactive site is called electrophile, that is electron seeking, and the reaction is called electrophilic. During a polar organic reaction, a nucleophile attacks an electrophilic center of the substrate, which is that specific atom or part of the substrate which is electron deficient. Similarly, the electrophiles attacks at nucleophilic center, which is the electron-rich center of the substrate. Thus, the electrophiles receive electron pair from the substrate when the two undergo bonding interaction. A curved arrow notation is used to show the movement of an electron pair from the nucleophile to the electrophile. Some examples of nucleophiles are the negatively charged ions with lone pair of electrons such as hydroxide, cyanide ions, and carbon ions. Neutral molecules such as H2O, R3N, R2NH, etc. can also act as nucleophiles due to the presence of lone pair of electrons. Examples of electrophiles include carbocations and neutral molecules having functional groups like carbonyl group or alkyl halides, where X is halogen atom. The carbon atom in carbocations has a sextet configuration, hence it is electron deficient and can receive a pair of electrons from the nucleophiles. In neutral molecules such as alkyl halides, due to the polarity of the CX bond, a partial positive charge is generated on the carbon atom, and hence the carbon atom becomes an electrophilic center at which a nucleophile can attack. Now 12.7.3, that is electron movement in organic reactions. The movement of electrons in organic reaction can be shown by curved arrow notation. It shows how changes in bonding occur due to electronic redistribution during the reaction. To show the change in position of a pair of electrons, curved arrow starts from the point from where an electron pair is shifted and it ends at a location to which the pair of electrons may move. Presentation of shifting of electron pair is given below. Here you can see first, second, and third. Movement of single electron is indicated by a single barbed fish hooks, half-headed curved arrow, for example in transfer of hydroxide ion giving ethanol, and in the dissociation of chloromethane, the movement of electron using curved arrows can be depicted as follows. Now 12.7.4 electron displacement effects in covalent bonds. The electron displacement in an organic molecule may take place either in the ground state under the influence of an atom or a substituent group or in the presence of an appropriate attacking reagent. The electron displacements due to the influence of an atom or a substituent group present in the molecule cause permanent polarization of the bond. Inductive effect and resonance effects are examples of this type of electron displacements. Temporary electron displacement effect are seen in a molecule when a reagent approaches to attack it. This type of electron displacement is called electromeric effect or polarizability effect. In the following sections, we will learn about these types of electronic displacements. Now the 12.7.5 inductive effect that I will cover in the part 2 of this chapter, and very soon I will upload the part 2, don't worry. बच्चों अगर आपको लग रहा हो कि इसने आपकी हेल्प करी हो तो इसको लाइक जरूर कर देना और दोस्तों के साथ में जरूर शेयर करना. टेक केयर एवरीवन, बाय बाय, सी यू सून इन द नेक्स्ट वीडियो. टिल देन जस्ट स्टे ट्यून्ड विद मी. बाय बाय, टेक केयर.